Hey everyone, welcome into lecture number 11 of the semester. This is on Euler and Hamilton paths. It follows section 10.5 in Rosen's text. So let's start this lecture off with a little motivational riddle, I guess you could say. But in the 18th century, you can read about this in the text. I'm just going to summarize it here. But in the 18th century, there was a city at that point called Königsberg. It's now called Kaliningrad in Germany. I'm sure I said that wrong. It's not in Germany, it's in Russia. That was definitely wrong, but Kaliningrad is probably also pronounced wrong. But here's the idea. There's a river called the Pregel River, and the Pregel River divides the city center into a couple of different, there's an island, and then there's a couple of different tributaries here. So I'm going to try to draw a picture of the way that the river looks here. And again, and I'm going to draw some bridges, and the bridges are the whole point. There is a much better picture in the book. So the river has kind of split here and gone around this island. And there's now 4 bridges for walking across the island. And at this point, it comes back together, and I have messed up my picture because there's another bridge. Whoops. To erase. There's another bridge here, so it comes together, but not really. There's another bridge here that connects to the other side. Like I said, you might just want to look this up in the book, but once I get this picture drawn, it should be okay. And then over here there are 2 more bridges. So the river kind of splits, comes back together, and splits again. All right, and like I said, this is called the Pregel River. Probably what I should have done is gotten a picture from Google Maps, and we could have tried to figure this out. Turn back time a couple hundred years, try to figure this out. But the idea is that these are bridges now, and so these bridges and the river itself have divided the city into 4 different portions now. So there's this island, which we'll call portion A. And then there are the 2 banks, B and C, on the 2 outsides of the river. And then there's this other, which in this picture looks like a peninsula here, another region D. But as far as the picture is concerned, that's probably going to be another island or something, right? So there's another D. And the story in the book says that in this time, in the 18th century, the citizens of, at that point, Königsberg, would walk around. They would walk around on Sunday mornings. So again, we're not sure where this story came from, but the idea is, though, that they would walk through the village, and they would trace out a path that goes across the bridges, all right? And so the question was, as 2 people are walking along, is it possible to walk across the whole city, cross all 7 bridges? All right, there's 7 bridges here. Is it possible to cross all 7 bridges and end up in the same place that you started? All right, so that's the question. So let's see if it's possible. This person could walk over here. By the way, this is like exhaustive method. Now I've got here. By the way, the question I didn't state properly, because the question is, can you cross each of the 7 bridges only once and then back up where you started? So by where you started is just regions A, B, C, or D, because from there you could, walk back. But now I need to take another bridge. So I've totally messed up this picture. But that's the question. Let me write down the actual question. So the question is, can you cross all 7 bridges exactly once? So no repeats on the crossing, exactly once, and end up back where you started. All right, and the person who answered this question is someone that I'm sure you've heard of. This is Leonhard Euler. So Leonhard Euler, in 1736, he answered so many mathematical questions of the day, right, that so many things are named after him. But Leonhard Euler in 1736 answered this question, and the way that he answered it was by converting the picture with the bridges into a graph where the bridges the bridges are the edges of the graph, and then the regions of the city that have been broken up by the bridges, those are the nodes. So the graph that he drew looks like this. So he's got 3 nodes here and 1 node here, and the way they're arranged is just like the way we've labeled this: A, B, C, and then D over here. So A, B, C, D over here, and then each of the bridges has to be represented by an edge. So there are 2 bridges between each of those, and then there's 1 bridge each over to D. So here's the graph. So he used this graph. So now, in the language of this graph, this question can be rephrased, okay? And so it can be rephrased to say, so the rephrasing, this is the whole point of this lecture today. The rephrasing says the following. So let me say this a little bit better. So rephrasing in the language of graphs, right? In the language of this graph is going to be the following. So is there a simple circuit? All right, is there a simple circuit? Remember, a circuit is a closed path, right? And a simple circuit is a closed path that uses only 1 edge each. So is there a simple circuit that uses every edge? So we can find a simple circuit, right? We can find a lot of simple circuits, but is there a simple circuit that uses every single edge? So this is the rephrasing. All right, and it turns out, well, I'll save the punchline. You can probably guess what the answer is based on if you have paused the video and you're tracing your own little person traveling across all these bridges in Königsberg in 1736. You know, that would be a fun way to spend a Sunday. But yeah, maybe you've got a guess as to what the answer is. But the answer, the question itself leads to a definition. So I'll call this item 2. So the definition that this is going to lead to is an Euler circuit. So an Euler circuit is going to be exactly a simple circuit that uses every edge. Okay, contains every edge of G. So an Euler circuit in G is a simple circuit. Remember, the word circuit means that the starting and ending vertex are the same, right, of the path. So it's a simple circuit in G that uses every edge. And the simple part says, you know, that implies that every edge must be used once, right? So as we get more vocab, our definitions can get a little sneakier, right? So uses every edge of G. There's a lot encapsulated in this definition, right? Simple circuit. Simple means every edge used once. Circuit means it starts and ends at the same point. And then uses every edge means, you know, every edge is used exactly once. So simple means at most once, right? And Euler, you can also define an Euler path. So an Euler path is just a path that isn't a circuit, but does use every edge. It's a simple path. It's a simple path. Again, simple meaning edge is used at most once. So a simple path in G that uses every edge in G. So the difference is that an Euler path does not have to be a circuit, right? It does not have to start and end at the same vertex. Okay, here's a theorem, and then from this theorem, I'm going to leave the proof as an exercise. I want you to read it because it's a very heuristic argument. It's not worth going through for me to like read it to you, but it's worth reading. So this one says the following. So a connected multigraph. So multigraph means you can have multiple edges between the nodes, right? A connected multigraph with at least 2 vertices has an Euler circuit. So this is an existence theorem, okay? It has an Euler circuit. If and only if the degree of each of its vertices is even. So the degree of each vertex individually. Remember, the degree is the number of edges that are adjacent, right? Or incident, I should say. Number of edges that are incident with the vertex. So the degree of each vertex is even. All right. Now, if we believe this, before we use this to say anything about our Königsberg problem, So the proof is an exercise. So I want you guys to read this. So read. It's really not a proof, actually. It's a discussion that leads to the statement of the theorem, but it spans the end of page 695, and it goes on to 696. So read those pages that lead up to this theorem. All right, so here's a result then. We can now answer our question if we believe this, which again, if you read the proof, you will believe it. It's just a heuristic argument. But we can now answer our question about the Königsberg bridge problem, right? Because the graph, we now have the graph, and look at the vertices. So what's the degree of each vertex? This one's 3. We're already done, right? We're already done. But well, let's do all of them just to be sure, right? Or just for completeness here. This vertex has degree 5. This one is 3, and this one is 3. So actually, this one does not have any even vertices at all. So it doesn't even have a subgraph that would have an Euler circuit. So there's our answer, right? So here's our result. I'll put a little arrow here. So there is no solution to the Königsberg bridge problem. And that's what Euler found, again, back in 1736. All right, so what goes along with this? Once we know that there's an existence theorem, so supposing we have, here's our theorem, right? Supposing we have a graph which obeys the hypotheses of this theorem, then we know that an Euler circuit exists, right? An Euler circuit exists. So the next question is, how can we find one? By the way, when one exists, it means there's at least one. There might be many, right? So the next thing is an algorithm. And I've copied this algorithm from the book. So an algorithm for finding an Euler circuit. So first of all, we are going to have a graph, right? G that obeys the hypotheses of that theorem. So let G be a multigraph whose vertices have degree, even degree, right? So each have even degree. And then I should have said, and the number of vertices is bigger than or equal to 2, right? So here n represents the number of vertices. All right, well, let me scroll down and get the algorithm. And paste it back up here, and we can look at it. So here's our algorithm. All right, so as we've looked at some of these before, this is directly from the book. It's from page 697 of the book, and maybe 696 or 7, one of those two. It's right after the theorem that we just referred to. As we've talked about before, in this book they call, you guys might be used to this, those of you who are CE majors of some kind. But for me, the procedures, this is the input, right? This is what you're going to give to, if you're going to actually write a program to find these circuits, then this is the input. And so what's the input? It's a connected multigraph. I didn't say connected up here, right? If it's not connected, there's no way to find a circuit like this. So it's obviously got to be connected. So there's our G, right? We put that in there. And the algorithm says to start with a circuit beginning at an arbitrarily chosen vertex with edges successfully added to form a path that returns to this vertex. This circuit does not have to be an Euler circuit, right? This is not part of the input, though. They're just defining what a circuit is, right? So G is so H is equal to G with edges of the circuit removed. Okay, so what does this say then? So while H has edges, this is all very heuristic, right? It's not code at all. So one of the exercises that I have written down here for you guys is to actually try to write this out. Try to make this systematically code this. But the idea is you choose a circuit, you remove the vertices, you then do what? A circuit H beginning of vertex H. So that's a subcircuit, right? You insert a circuit at certain subcircuits. So yeah, how does this work exactly? So what does it say to do? It doesn't say anything about this circuit having to be an Euler circuit, right? Successively added to form a path that returns to this vertex. Arbitrarily chosen, though, right? So arbitrarily chosen. And so H is equal to, and it's a new graph with the edges of the circuit removed. So while H has any edges at all, then you find a subcircuit. So subcircuit is going to be a circuit in H beginning at vertex H, at a vertex in H that also has an endpoint of an edge of circuit. All right, so this vertex has to share an edge with circuit, right, with the original circuit. And then what do you do with H? So H then you update. So it's now the edges of subcircuit and all isolated vertices removed. So isolated means they don't have any, they're not connected at all, right? So those are removed. And then circuit is circuit with subcircuit inserted at the appropriate vertex. So as a recommended exercise, try to make sense of this. So recommended exercise here, make sense of it. It's supposed to result in an Euler circuit, right? How can that be based on this? Well, there's got to be some subtleties about the way this is worded, right? So make sense of this and write at least some pseudocode, but write some code to actually compute it, so to actually run it. All right, and I might make this like an extra credit project because I think this is a very good exercise. So try to do this for sure, especially if you are a CE major, which I think most of you guys are. So it's probably not as difficult for you as it would be for someone like me. But when you do this, you have to, if you're going to write code, to actually do it, right? As opposed to just an algorithm that, you know, does not seem even conducive to coding right now, the way that this is written. You have to find a way to represent your graph G, right? So you have to have your graph, your edge set, your vertex set. Everything has to be defined in appropriate ways. And then you have to run the algorithm in a way that is, you know, compatible with the way that you've defined your graph G, right? So we'll come back to this one probably as an extra credit assignment, but we will come back to this one at some point because it's interesting. All right, a couple more things to talk about. There's not too much more in this lecture, but let's talk about it. So here's a theorem, another theorem. This one says that a connected multigraph has an Euler path. So again, we have a connected Euler graph now. Oh, sorry, a connected multigraph. All right, this one is going to have an Euler path, but not an Euler circuit. So, but not an Euler circuit. If and only if, again, this is an existence theorem, all right, if it has exactly two vertices of odd degree. All right, so the key here is exactly two. It can't have more, it can't have less. All right, so for this one, I have another image down here that I want to look at, and we can try to figure out if any of these have Euler paths, but not circuits. So as I scroll up here, let's paste this here. All right, so this is figure 7 from the book, but we're just going to look at it now. So all you have to do to use this theorem is to find the degrees of each vertex, right? So this vertex has degree 2, this one's 3, this one's 2, this one's 3. That's exactly two of them that are odd, right? So this one should be a yes. If it's a yes, then we should be able to find it, right? We should be able to find it. So if it has, so the idea here is that it should have an Euler path, but not an Euler circuit. So an Euler path means that we go from vertex to vertex, right? So we can go, say, this way, this way, this way. The order doesn't matter, but I'm going to make it, I mean, it kind of matters, right? And as we travel along, we started here, we ended here. And so that's an Euler path because we traveled each edge once, but we did not end up at the same vertex, right? Okay, so that's how this works. And then you can go through and find these. This one's going to be a no because you can see right here, 1, 2, 3, you're done, right? There's 4 of them actually, that 5 of them, 6, 5, 5 of them that have odd degree. So this one's going to be a no. That does not have an Euler path. And obviously it can't have an Euler circuit either because it has some vertices of odd degree. This vertex is not of odd degree though, is it? This is a 4. So maybe I've jumped the gun. I started counting too quickly. This one is going to be a yes, actually. Right? So what do we have? We should write this down. Don't try to cheat it. So there's a 2. This one has 3. This one has 1, 2, 3, 4. This one has 1, 2, 3, 4. Right? Same here. 1, 2, 3, 4. This one has 3. This one has 2. So actually I jumped the gun. This one's a yes, right? This one is a yes. This one has exactly 2 vertices of odd degree. Okay. So, what about this one? This one, all the outer vertices are 1, 2, 3. That's for all the outer ones, right? So this one's going to be a no. Once you get to 3, this one's a no. All right, and none of these have an Euler circuit because to have an Euler circuit, you have to have all even degree. That was our theorem up here, right? And so there you go. There's an example with those ones. All right, one more thing to discuss here. This is, we'll call this a definition. A simple path now, so a simple path in a graph that uses every vertex exactly once is called a Hamilton path. So a simple path in G that uses every vertex exactly once. Same deal, right? Exactly once is called a Hamilton path. And there are a couple of existence theorems for this as well. So, first of all, here's an exercise that I highly recommend. Hint, you might see this one again. All right, so prove that every complete graph K sub n, for n greater than or equal to 3 in this case, has a Hamilton circuit. So how can you have a Hamilton circuit, right? Well, so we have to change the definition a little bit. So in this case, a Hamilton circuit is a Hamilton path if you delete the last vertex, right? So it's a Hamilton path except that the first and last vertex coincide. All the other vertices happen only once. So the rest of them are only used once, right? Okay, so you can prove this. By the way, there's a couple different ways to prove this. You can, yeah, I'll let you think about it though, but there's some information in the book, so you'll be able to find, if you look that up in the book, you'll be able to find information on that one. So here's the last item for today's lecture. A couple of existence theorems for Hamilton circuits. So existence of Hamilton circuits. One is a little weaker than the other, meaning it's weaker in the sense that you actually need more, it's less precise. So less graphs satisfy this, but that's okay. So there's two theorems, and they're named after two mathematicians. The first one's called Dirac's theorem. And this one says the following. So if G is a simple graph with at least, so with n vertices and at least 3 of them, all right? So n vertices with n greater than or equal to 3, such that the degree of each vertex, so this is similar to our theorem for the existence of the Euler circuit, right? But so far, it's going to be a totally different result, but such that the degree of each vertex is at least n over 2, all right, then G has a Hamilton circuit. So our G will have a Hamilton circuit at this point. All right, the other theorem is a little stronger. This is Orr's theorem. And this one says, so kind of the same, so same G. So in this case, G will be a simple graph. N greater than or equal to 3, that's the number of vertices, and what? Same deal, right? So this time, here's the condition, right? So such that the degree of U plus the degree of V is greater than or equal to N for all non-adjacent vertices. So for all pairs of non-adjacent vertices. Then what's going to be true? Then, so the U and the V are the vertices, right? The non-adjacent vertices. Then G has a Hamilton circuit. All right, and so it turns out, so again, recommended exercise, this one's going to be listed as one of your homework assignments, but the proof is outlined in exercise 65. So exercise 65 outlines the proof, so make sure you work through that problem. So this is the proof of Orr's theorem. And then, as a recommended exercise, you can do this first, actually. Suppose you believe Orr's theorem, so in other words, assume Orr's theorem holds, then Dirac's theorem is a corollary. And so use corollary. I spelled it wrong. There's only one R in corollary. I'll rewrite it. So corollary. So I want you to write that out, right? So write the proof. It's very simple. So assuming Orr's theorem holds, prove Dirac's theorem as a corollary. All right, so the end of this section is just a couple of examples and not even examples, but example applications. So make sure you read through those. Let's read example applications right before the exercises, and I'll see you guys in the next lecture.